Welcome friends. Today we will be discussing another example when we can use backtracking to solve a computational problem. Now the problem at hand is known as sum of subsets. Now as you can see on the slide, the sum of subsets problem basically deals with when we are given a set of n distinct positive numbers, often called as weights, and we have to find all possible combinations of these numbers whose sum is equal to other value. So we have two inputs, one is the set of positive numbers and another input is a sum, okay, to which we have to verify and find all possible combinations from that input set so that the sum of those numbers matches that particular specified sum, which we refer to as m. In the example you can see we have this set specified as 1, 3, 5 and 6. So we have 4, n is equal to 4, the numbers are 1, 3, 5 and 6, and the specified sum m is equal to n. So we have to find all possible combinations of 1, 3, 5 and 6 whose sum is equal to 9 in this example. Now it is obvious there are simply two sets or two combinations which basically yield the sum 9, and you can see it is 1, 3, 5 and other possible combination is 3 and 6. There are two ways of giving the solution, this possible set of combinations for this sum of subsets problem. One is referred to as a variable size tuple solution and another one is a fixed size tuple solution. Now in the first example you can see the size of the sets is variable. So the first set includes 1, 3 and 5 and the second solution set includes 3 and 6. So the size of these sets is variable. Another way of representing the same solution would be using the fixed size tuples solution. Now in this solution each solution set has the same number of elements, or the number of elements in each solution set is equal to n. That is the number of input elements. As you can see in the second case, the number of elements here is equal to 4, which is basically the number of elements that we had in our set, and the second solution also has the number of elements equal to 4. But the difference here you can observe is the values that these sets can take, or the elements in these sets, can only be 0 and 1. Now what do they basically mean? An element in any of the solution vectors, for example let's consider this solution vector here, x1, okay, this is x2, this here is x3, this here is x4, okay. So we refer to the elements in a solution vector as xi, okay, x1, x2, x3, and xi will be equal to 0 or 1 depending upon whether its corresponding weight, which is referred to as wi, is included or not. The weights in our case in the set where w1 is 1, w2 is 3, w3 is 5 and w4 is 6. So this solution vector here, 1 here means that we are including weight number 1. Similarly 1 here means that we are including weight number 2, because this is x2. x3 is equal to 1 also. This here means that we are including weight number 3, and the 0 here means we are not including weight number 4. So obviously the sum here is equal to 9, and that is the required sum, and same applies to the second vector as well. And in our examples that we will be discussing in this lecture, we will be considering this fixed size tuple solution. You can generate variable size tuple solutions as well, it's not so much different. Now if we consider the state space tree of the example that we discussed previously, as you can see we have mentioned on the slide that for any node at level I here means corresponding to weight number I. For example, level 1 means weight number, we are talking about weight number 1, level 2 means we are talking about weight number 2, and so on and so forth. So for a node at level I, or for example a node at when we are considering weight number, for example 1 or 2 or 3, weight number I, the left child corresponds to xi is equal to 1. It means, for example, if we take this node here and we have to consider the decision has to be made for weight number 2, this is for weight number 2, okay. The left child for this node, so x2 is equal to 1, means that we are considering this weight number 2, and the right child referring to x2 is equal to 0 in this case means that we are not considering weight number 2. Similarly at any node, for example at this level number 1, 2, 3 and 4. So for this node the left child here means we are considering weight number 4, okay. The right child here means we are not considering weight number 4, and so on and so forth. So we will stick to this notation, and as you can see on the slide, it's a full state space tree that can be generated to find solutions for the sum of subsets problem. And the solutions here are marked as green. As you can see here, this is one of the solutions, this is one of the solutions, and this is one of the solutions. Okay. Now, how do we get a solution? We have to follow the path from the root, as we have done in our earlier cases, to a solution node. Now, if we had stopped at this point, then we were considering variable size solutions. Okay. But if we have to move to the leaf nodes, that is how we get the fixed size vectors or tuples. Okay. So, we will be considering fixed size tuples. So, finding a path from root to the leaf, okay, and considering the presence or absence of a weight in our solution. So, 1 here basically means we are considering weight number 1, 0 here means a solution where we are not considering, for example, weight number 1. Similarly, if we consider this path, this means we have not considered weight number 1, we are considering weight number 2, we are not considering weight number 3, and we are considering, for example, weight number 4. This sums up to 9, because weight number 1 is 1, weight number 2 is 3. So, we are considering 3. So, 3 plus 6, which basically yields 9. So, now using backtracking, if we want to solve this problem, it is obvious that we need some kind of bounding functions, okay, so that we can restrict, because if you can as you can see, if the problem size increases, the size of this state space tree will also increase, and finding the solution by traversing the complete state space tree again is kind of time consuming. So, it would be better somehow if we are able to restrict our search in the state space tree, so by bounding our traversals. So, as in the earlier cases, we somehow need certain bounding functions for this sum of subsets problem as well. Now, one of the first cases that we will be considering for our bounding functions is that Bk, for example, stage at level k, okay, we have considered, for example, weight 1, weight 2, weight 3, up to so on up to weight k. The bounding function is equal to true. Okay, so it means we will continue using this partial path to reach the solution path. Okay, is equal to true. The first case would be if the summation of the weights so far that we considered, considering xi to be either 0 or 1, as you can see, as I discussed earlier. So, 1 into weight would be considering the weight, 0 into the weight multiplied by the weight means we are not considering the weight. So, what we are saying here is the first case for our bounding function is the sum of the weights that we have considered so far plus sum of all the remaining weights has to be greater than or equal to m. Okay. As an example, these are the input weights that we have. So, this is the weight vector, weight 1, weight 2, weight 3, weight 4. Okay. In our earlier example, we took weight 1 equal to 1, weight 2 is equal to 3, weight 3 is equal to 5 and 6, and so on and so forth. Now, let us suppose for the time being we are at weight number 2. So, k is equal to 2 in our case, and we have considered these weights. So, weight 1 is considered, okay, and weight 2 is also considered. Okay. Now, we will continue using this path to generate or to search a solution path only if this condition is satisfied. What it says is the sum of the weights so far, that is the weight so far is k is equal to 2. So, sum of the weights so far from 0 to k is considered to be 4, because 3 plus 1 is equal to 4, and plus this summation, which is a sum of all the remaining weights. So, from k plus 1 to n, okay, sum of the remaining weights, which is equal to 11 in this case, it has to be greater than or equal to m. So, if we compute this, so 4 plus 11 is greater than 9. 9 in our case, as I'm talking about the previous example, the sum that we have to consider is 9. So, in this case, if we have chosen x1 to be equal to 1 and x2 is equal to 2, whether we should follow this path to find a solution or not, the bounding function in this case, as we discussed here, is true. Okay, it is a requirement. Let us consider the fact that we have considered weight number 1, we have not considered weight number 2, and we have not considered weight number 3. This is a small example, you can test it on a larger example. Then this condition is obviously false, because the weight so far is equal to 1, okay, and the sum of the remaining weights is equal to 6. Okay. The sum of the first case and the second case is equal to 7, which is not greater than or equal to 9. It means that we will not be using or following or continuing with this subpath to find the solution to our problem. Okay. So, this is one of the examples. this is the simplest bounding function that we can use to kind of find or restrict our search in the state space tree, as was shown earlier. Now we can further enhance the bounds by considering the fact. So if we assume that the weights, that the input weights are arranged in non decreasing order, then if we consider a vector partial tuple for the solution, let's suppose x1, x2, x3 up to, let's suppose, xk, okay, if this is the partial vector, then it would be obvious to say that this vector or this partial solution cannot yield an answer if the condition here is true. What does this condition basically say? It says the sum of the weights that we have considered so far, okay, plus the immediate next weight have to be or greater than m. What I am trying to say here is, if the sum of the weights so far that we have considered and or not considered, whatever weights we have considered so far, for which xi is equal to 1, the sum of those weights plus the immediate next weight on which the decision has to be made, okay. If it is greater than m, if the sum of these two terms is greater than m, then obviously we cannot get a solution, because if we keep on adding other weights in the sequence, the value will always be greater than m. It can never be less than or equal to m, okay. If the immediate next weight sums up to a value which is greater than m, then we cannot find a solution if we keep on continuing with this partial vector. Let's consider this example as is shown on the screen. Now the weights here are changing. Now earlier this the first weight was 1, now it's changed to 2. So let's suppose these are the weights 2, 3, 5 and 6 are our weights, and the solution vector or the vector so far that we have, or the tuple so far that we have partially generated, is x1 is equal to 1 and x2 is equal to 1. So the sum of the weights so far is simply equal to 3 plus 2, which is equal to 5, and sum of the immediately next weight that we have to decide whether to consider or not, which is w of k plus 1 here in our case is 5, this 5. So the sum here is greater than 9, okay. Now since it is greater than 9, it means we cannot continue with this vector or with this tuple, and we won't be able to get a solution with if we follow this particular tuple. How? If it is a simple observation, so far the sum is 5, okay. If we consider another weight 5, the sum is equal to 10, which is greater than m. If we consider it to be 0, okay, still we will not be able to find a solution if we take this as 1, okay, because the sum would yield to 11, which will always be greater than m. Or if we do not consider this value as well, or this total weight that we will get, if we do not consider any of the weights after k, will again not be able to get a value equal to m. It will be less than m. If we consider any weight greater than k, it will be greater than m. So it means we can stop right here. So it's simple to stop right here and not to proceed with finding solutions to by considering other weights, okay. Similarly, in this example here, if the vector so far, or if the tuple so far is x1 is equal to 0, x2 is equal to 1, x3 is equal to 0, okay. If we test this with this this condition here, k is equal to 3, okay. Sum of the weights so far is equal to 3, the corresponding solution value here is 1 for the time with the partial solution. So we are considering 3, 5 we are not considering, so the sum of this weight so far is equal to 3. Now the immediately next weight that we can consider is 6 here, okay, the immediately next weight, and the sum of the 6 and the weight so far is equal to 9. So it is less than or equal to m, okay. So we can consider this solution here, we can treat this as 1, okay, and continue finding the solution. So in this case obviously we have already found the solution because the sum of 3 and 6 is equal to 9. This is a small example, you can work it out on a larger example. So from this second case we can formulate a condition as is shown on the screen. So our bounding functions are, if the sum of the weights so far plus sum of the all the remaining weights is greater than or equal to m, then it is possible that we might find a solution. Similarly, if we assume that the weights are initially in non-decreasing order. This is important because if they are not arranged in this order, then this condition cannot be considered. Okay, in that case, sum of the weights so far that we have considered plus the immediate next weight that is available to us, if we can only find a solution or continue finding a solution, the sum of these two terms is less than or equal to m. Okay, so we'll use these two conditions to formulate an algorithm for the current sum of subsets problem. Now, in order to design the algorithm, we will use a couple of terms here. One is weight vector or an array from values 1 to n, which we are assuming that the values in this weight array are arranged in non-decreasing order, and also the first weight, that is w1, has to be less than m, okay, and sum of all the weights in this array has to be greater than or equal to m. These are the initial conditions that we are relying upon, otherwise this algorithm might not work correctly. Now, the solutions will be saved in this array x, which has again elements from 1 to n. As I told you, we will be considering a fixed size tuple solution. Okay, and we are referring to this term. You might remember this. This is basically, let's suppose we are at level k minus 1. Okay, so then S, we are saving the sum of the weights that we have considered so far. So this S would be initially 0. Similarly, R is equal to sum of all the remaining weights after from k to n. Okay, and initially R is equal to sum of all the weights, because as I said, initially we will be taking k is equal to 1. S in that case would be 0. Okay, we have not considered any. K here means the decision on which the level number at which we are taking the decision right now, whether to include the weight or not to. So initially S would be equal to 0, and similarly R would be equal to the sum of all the weights in the array. Okay, that is how we will be calling our function, that will be algorithm that will be discussing shortly. So we remember that this array contains weights in non-decreasing order. This is where the solution will be stored. Similarly, S would store some of the weights so far that we have considered. R would be storing a value which basically tells us some of the remaining weights up to which we have already kind of considered. So if k minus 1 is the point or the level that at which we have taken a decision, from k to n we are considering remaining sum that we will refer to as. Now, on the screen is a complete algorithm of the sum of subsets. It takes 3 parameters. This is S, that is the sum of the weights so far. R is the sum of the remaining weights, okay, and K here is the level number at which we are currently taking the decision. Now, as I told you that this function would be called with the values S is equal to 0, K is equal to 1, and R is equal to sum of all the weights in our array. Initially it will be called like that. So we'll go through the statements one by one and see how it basically works. Now, as soon as we enter this function here, we are generating the left child. Now, why are we generating the left child? As I earlier told you, generating the left child here means that we are considering the kth weight. Okay, the k here is 1. So initially we are considering kth weight. Why is that so? Because I already told you S would be initially 0. Okay, W of k is equal to 1. So W of 1 is less than or equal to m. This is the basic condition that I told you earlier. Now, why is that so? Because for this condition, for the initial state, the bounding function would be true for k minus 1. We will later on see how it will be true for every entry to this particular function. Whenever we enter this function, b of k minus 1 would always be true. So we can consider the kth weight. Since we have to generate the left child, okay, it means that we are considering the current weight. It means k, whatever the current value or the current level or the current weight number, the solution array x, we have to store 1 for that particular weight. So if k is equal to 1, so x1 is equal to 1. Okay. Now, if the sum is equal to m, it means we have found the solution or the solution vector. We can simply display that particular solution vector. So if the sum so far S, so is, as I said, would be the sum of the weights so far plus the current weight. If the sum that we have considered so far, that is passed as a parameter to this particular function S, as I earlier told you, plus the current weight that we are considering is equal to m. Okay, then we simply write the solution, then we write the subset. Okay, so up from 1 to k. Now obviously you might see that it might in certain cases display a variable size solution, but you have still got the idea that the values would be 0 or 1 for that case. Now if this is not the case, it means we have not found the solution yet, but we have considered the current weight. Okay, there are two options for us: either we have to consider the next weight or not consider the next weight. So whenever we enter this particular function, we are considering that the current state or the current level satisfies our bounding condition. So we consider this kth weight. Okay, and if by considering this current kth weight, if we have found the solution, then we will simply write it. However, if we have not found the solution yet, then we will have to continue by generating the left and the right childs for this particular current node. Now whether or not we have to generate the left or right child, or whether or not we will continue using this current path or not, we will have to check the bounding conditions, and that is what we are doing here. Now if we have not found the solution, then if the current sum plus the current weight, so let us represent this as the weight so far, because we have considered weight number k, as you can see there. So the weight so far plus the immediate next weight, okay, this is the second condition of our bounding function, is less than or equal to m. Okay, then we can continue with by considering the other weights or the next weight in line. So we make a recursive call here. Okay, then sum of subsets, the S here would be passed S plus Wk, which adds to the previous sum so far plus the currently considered weight. Okay, so this would form the new sum so far. K plus 1 here means we increment the level. Okay, we have taken a decision for the k plus 1th level, because for k we have taken a decision, and the remaining weight R now as the parameter would be passed R minus the weight that we have considered. Earlier, as I said, for the first call, this R is equal to the sum of all the weights that are in our weight array. Okay, now in the consecutive calls to this particular function, this R value would may be decreasing if we are considering the weights as we go along these calls. So if we have considered a weight, we will be decreasing or subtracting that from R and passing that weight or the remaining weight to this function again. So this is the case if we can continue with the left child. Similarly, we have also to consider the fact that the next weight may or may not be considered, or the value for xi for wi may be 0 as well. Okay, so we'll evaluate bounding condition, the first case in fact of the bounding condition. So sum of the weights so far that we have considered plus R minus Wk. Now this here means that we are not considering Wk. Here the first case we said we considered x of k is equal to 1. So for this case we are considering this weight. Okay. Now there is also a possibility that we may not consider this weight and see whether we will be able to get a solution or not. So what is considered here, if the sum so far plus R minus Wk, okay, this minus here basically is that we are not considering Wk from rest of the sum. Now it has to be greater than or equal to m. This is the first condition of the bounding function that we just discussed earlier. So this is the first one. Okay. Now there is also a second condition, sum of the weights so far plus the next weight in line. So we are testing both the bounding. This is the first condition of the bounding function, and this is the second condition of the bounding function. Here we are verifying that if we are not considering the current weight, the sum of the weights so far plus sum of the remaining weights has to be greater than or equal to m. This is not the only condition that we need to test. We also need to test the second condition, that is the sum of the weights so far plus immediate next weight that we have to consider. Now k plus 1th weight, okay, we have not considered kth weight, so we are considering k plus 1th weight. Now this has to be less than or equal to m. If this is not, again as I earlier told you, we will not be able to find a solution. So both these conditions are tested here, and if they are true, then only we'll be considering kxk is equal to 0. So not considering this case but considering the other cases, or not considering this weight but considering the other weights, and we'll make a recursive call here as well, sum of subsets. we, in this iteration, if this is the case that we are taking xk is equal to 0, we are not considering the current weight, nothing will be added to the weight so far. So s is passed back to the next call as it is. K plus 1, for the next level we have to choose, or for the next weight we have to make a decision whether to include that or not to include that. In fact, we are considering both the cases. We are including as well as we are not including. As you can see here, we are including a weight, here we are not including a weight. Whatever path finally takes us to this case, okay, if we are able to find the sum, well and good, we'll just print the solution so far. If we are not, then we'll simply bound our branches in the state space tree, or the searches in the state space tree, by verifying these conditions here. So we are passing k plus 1, so it means the next level, or the next decision, we have to take the next decision. Okay. The remaining weights would be r minus wk. It means we are subtracting this weight that we just did not consider from the remaining weights, because we have not considered it so far and we will not be considered it later as well. So the remaining weights would again be decremented by the weight that we were just considering. Okay. Although we have not considered that, or we have not used that to find the sum, but it will still be decreased from the remaining weights. Now this is a very straightforward algorithm. You can work out this on a smaller problem or a larger problem and see how you maintain these arrays, this x array, okay, and the values, how do they change, this s value, this r value. It will give you a good idea of this, how this backtracking basically works. Now we have just roughly tried to dry run the earlier which states in the state space tree are bounded using this backtracking algorithm. So this is the array, this is the input array, this is the weight array here. As you can see on the slide, we have weights 2, 3, 5 and 6. So k is equal to 1, s is equal to 0, r is equal to sum of all the weights, which is equal to 6 plus 5, which is 11, 14, 15 and 16. So r would be equal to 16, s would be equal to 0 and k would be equal to 1 for the first time when we first run it. So we will be, as you just need to tally it with the function or the subroutine that we, or the algorithm that we just discussed. You will see it will be in line with that. So x1 is equal to 1. So the first statement, first couple of statements in that particular algorithm. Similarly, since we have not yet found the solution, there will be another call to the same and the condition would be verified. So the weights so far are 2 plus 3, which is equal to 5. Okay. And let's suppose m is equal to 9. In this case, m has to be equal to 9. So only be continuing with another call here to generate the left tree if the sum so far is 5 and the sum of immediate next weight is less than or equal to 9. As you can see, the current sum is 5 and the immediate next weight is 5. Sum of these two weights is greater than 9, that is supposed to be equal to m. So we will not be generating a left child for this. Same applies to the right children. Okay, one of the conditions does not satisfy. For example, sum of the weights so far plus r minus wk, if you are not considering this current node, okay, has to be greater than or equal to m, and sum of the weight so far plus the immediate next weight, okay, has to be less than or equal to m. So in this example here, let's suppose we are not considering k so far is, let's suppose, 2, okay. A left child cannot be generated, and the same way a right child can also not be generated, because the sum so far is 5, and if we are not considering, let's suppose for example this x3, okay, we are not considering x3, 5 plus 6, the remaining weight is 11, sum so far is 5. So if we are not considering this weight w3, then 5 plus 6 should be less than or equal to m, but it is greater than m, because 5 plus 6 is 11, but m is equal to 9. So obviously we cannot generate either the left or the right children of this node, so we'll simply bound it. Similarly, you can see for example in this case for 7, so far we have considered weight number 1, weight number 0, weight number 7, we are at this particular point, considering that we are at this particular point. Now can we generate the left child? Okay, k here is 4, because we are taking a decision for 4. So we have to verify whether the sum so far, which is 7, plus weight of k plus 1 are less than or equal to m or not. So in this case, obviously the sum so far is 7, as you can see, and the remaining weights is 6. So 6 plus 7 is equal to 30. So again, this value is greater than m, so left child will not be generated. Similarly, same applies to the right child. For this particular node, from the conditions you can verify that we are not able to generate a right child as well, because one of the conditions, the bounding functions, is not satisfied. So we'll simply bound it, and as you can keep on going, we'll see that this node is also bounded here because it also does not satisfy some of the conditions. And finally, the only path that is generated for this case is this one. Using our algorithm, you can simply follow the steps for this particular example where the weights are 2, 3, 5 and 6, and you will simply see that this is the solution that we'll get. Hopefully you are able to understand how this particular algorithm works, and it would be work out this algorithm and this concept on a larger problem and see how the search in the state space tree is reduced, how the bounding functions basically work, how time is saved using this backtracking algorithm. This would be it for today. In the next lecture, we'll be discussing the last example that can be solved using backtracking, and we'll see 0-1 knapsack problem. How 0-1 knapsack, you might have already discussed or studied this 0-1 knapsack problem, tried to solve it using some other computational methods, but we'll see how we can solve this 0-1 knapsack problem using backtracking in our next class. Till then, thank you. Thank you.